This is chapter 2 of our discussion of EE130, feedback control system. So we're done with chapter 1, the review for Laplace transform. So chapter 2 will be about transfer function. So what is a transfer function? A transfer function generally uh, is a mathematical model of a certain system that relates the output of the system to its input. So if we have a system, so this block represent our system, we can model this one into a transfer function. Usually name it as G's of S. And transfer function usually in the S domain. So we need to apply Laplace transform if we're given a time domain function, then we convert it into S domain. So if we apply an input to this transfer function or this model or this system, let's say we name our input as R. So this is our input. Then it will result to a certain output C, C's of S. So to model this one transfer function, it's just equal to the ratio of the output and the input. So this is just the output all over the input R's of S. And it's just the ratio in S domain. And that's the transfer function. Now, there is a procedures in finding the transfer function. First, we need to identify the input and also the output of the system and output. So that's the first step. You need to know what's your input, you need to know what's your output if you're given a system. Then next, we can start modeling if you know the output and the input by applying techniques or concepts or laws. Techniques, concepts, or laws in circuits or electrical network for mechanical system in physics or kinematics to derive the differential equation, to formulate a differential equation. In this one will be in T domain or in time domain. Time domain. So the function here is with respect to time. That's the problem. The real problem should be in time domain. Then after deriving the equation, you now have your equation based from the techniques that you want to use. We need now to convert that equation, convert to S domain, to the frequency domain or S domain by taking the Laplace transform, by Laplace. Taking the Laplace transform of that. Then after taking the Laplace, you can now rearrange the equation algebraically in the form of a transfer function, which is the output over input, C of S over R of S, or output divided by the input. And that will be the transfer function. So the first one that we will be looking at, we have different type of system. We have the first one, we call it the zero order system. Zero order systems. So these are systems that does not contain an element that stores energy. In other words, this means that the output is changing linearly with the input. So proportionally, it's constant. It's a linear relationship between the output and the input. Then that is a zero order system. In electrical system, the very basic example of this is the voltage divider circuit. If you have two resistors here, then you have an input. Let's say this is our input voltage, E in, or we can just use V's of in, VI in T domain. And we have, this is R1 and R2, and we can let our output to be the voltage across this resistor 2. So V out and T domain. So our input, so first procedure, identify the input and output. So input is this one, the voltage, and output is this one, the voltage across R2. You can change it if you want. If you want the voltage across R1, it can also be the current passing through R1 and R2, the total current. So now, what will be the transfer function of this system? So to do that, we apply the theorem in circuits, electrical circuits. That's voltage divider theorem. And that V out, the voltage across that resistor, R2, is just equal to the total voltage, which is the V input, and you multiply it with the resistance here. We are solving for V out, the voltage across R2, so R2, all over the sum R1 plus R2. And this is the number 2. We already applied. There's no differential equation, but this is in time domain because there's no storing element in the circuit. So there's no, it does not change with respect to time. It's constant. Now we apply the Laplace at both sides. So to apply the Laplace, this will just become capital V's of out. In S domain, this will become S domain, and this are just constant R1 plus R2. Then rearrange. So the transfer function now of a voltage divider, G of S equals the output all over the input will be equal to this one, R2 all over R1 plus R2. So this is how we find or determine the transfer function of a given system. So this is a basic example. Another main application of a zero order system is the one that we call non-inverting op-amp. Non-inverting. We also have the inverting op-amp. Let's take a look at the first one. You already discussed this, operational amplifiers in your circuits 1. Circuits 1. So you already know what are the characteristics of an ideal op-amp. So we will be doing ideal analysis for an op-amp. So if this is the op-amp, and this is negative, positive, then we have an output here. Then we have an input that is connected to the positive terminal of the op-amp. So let's call this one VI in T domain. We have output in T domain. Then we have a feedback here, feedback resistance. Let's call it R2. Then another resistance here. Let's call it R1. And this should be connected to ground. So this is an example of a non-inverting op-amp. Now our first step, we identify the output. This is already our output, the voltage here, and the input, the voltage here. So these voltages here, V input and V out, these are all with respect to ground. So when you see just one terminal, it means the other terminal is connected to ground. So this is positive, the negative one is connected to the ground. Also this one, this is positive, this is negative, and this one is connected to ground. So I don't need to write them all. It's automatic that is connected to ground, the other terminal. So one characteristic of an ideal op-amp is the input impedance. The input impedance here, if you look back, the looking back resistance should be infinite. So this means there's no current flowing through at this point. The current here is just equal to 0. And also the voltage here is the same as the voltage connected in the positive. So this is also our V input. That's what we call the ideal op-amp, because the difference is very, very small, and this voltage is also the same as that voltage. Then what are the currents here? We have, by applying KV, or we can just apply nodal analysis. We have a current flowing through in this direction. We have a current flowing through in this direction. I can name this one I1 and this one I2. And we know that I1 should be equal to I2. Or we can just make it in that direction. I1 should be equal to I2 by applying KVL here. We have, so that current here is the same as the current here. It's just equal. I1 is just equal to I2. But what is I1? I1 is by applying nodal analysis. So the voltage here minus the voltage here. What's the voltage here? This is connected to ground. So the voltage there is 0. So this will be V input minus 0 all over that resistance R1. For I2, we start here. So V input, then going toward at this point, and that is just V output. So minus V output, and this is all over R2. Then rearrange, or we can apply now Laplace if you want. So this will be V in the S domain all over R1, and this will be 1 over R2 times V in S minus V out in S domain. Then cross multiply. This will be equal to, or we can move that V input at the other side, or the V out now will be equal to 1 over R1 V in plus 1 over R2 or wait, this should be 1 cross multiply, so this should be R1 over R2 times multiplied R V in R1. Then if this should be R1 times or R2 over, or let's just make it 1 by 1. So V in, this will be R2 or R1 over R2 cross multiply times V in minus R1 over R2 minus V out. Or wait, there's the minus here. R1 over R2. If we distribute that R1 over R2, then if we put V out at the other side and V in at the other side, so we have R1 over R2 V out is equal to R1 over R2 V in plus V in. Then we want to solve V out over V in by dividing both sides by R1 over R2. So V out, and we can factor out V in here. So we have R1 over R2 plus 1. This is all over R1 over R2. And this is V in. Then V out over V in, because we want to remember the transfer function, G of S is just equal to the output divided by the input. And if you do that, this one will be equal to, so at the numerator, this is, if you add this R2, R1 plus R2, then you divide this with R1 over R2. And R2 will cancel out, so it should be R1 plus R2 over R1. So R1 over R2, R1 plus R2 over R1. And if we divide this will become 1, and it will become R2 over R1. So this is just 1 plus R2 over R1. So this is the transfer function of a non-inverting op-amp operational amplifier. For an inverting op-amp, a zero order. Take note, these are zero order because the output, these are just constants. The transfer functions are just constant. Non-inverting op-amp So this is the circuit of an inverting op-amp. The negative now is connected, or the positive is connected to ground. This is our out, and this is our input, V in. And we have a feedback. This is our output. This is R1, R2. Then you repeat the process again. So this is ground. This voltage here should be also equal to 0 because that terminal is connected to ground. This is what we call the virtual ground. Then we can apply, again, the current here is the same as the current here. Then repeating the process, because this is 0, V in minus 0 divided by R1. That's the current. So V in minus 0 divided by R1, and that is equal to 0 minus V out all over R2. And taking the Laplace, so we have V in all over R1 equals negative V out all over R2. And V out over V in, then this is negative, so G of S, or V out over V in, is now equal to negative R2 over R1. So this is the transfer function of a non-inverting or an inverting op-amp. It's negative because inverting, the op-amp is inverting. Then this is for electrical system. In mechanical system, mechanical system, a very good example for mechanical system, a zero order, is this is a spring. If we have two springs here, it's connected to if this is a massless body, massless, this means the mass of this is negligible. Then if we apply a force in time domain, so that will be our input, then the result will be, of course, this will move into that direction, the displacement x of t. If this is k and this is also k, the spring constant. So what will be, if our input is f, this is the input, and the result will be this one, output. What is the transfer function of this system? Remember in physics, if two springs are in constant, we can simplify them into just one, just like a resistor in parallel or inductor in parallel. And that equivalent will be just the sum of the two. And k plus k is just equal to 2. So the equivalent spring constant of the two will be just twice k. So if we solve for the transfer function with the input f of t, so this will be just equal to the formula for the force applied in a spring constant. We know that F, or the force F, is just proportional to the displacement x if this is in time domain in physics. So if you use this, F of t is just equal to the k, the constant, which is so this is F equals k times x, where k is the spring constant. We call it spring constant in physics. So this one will be, because it's 2k here, so it's, we multiply it with 2 times k. Because they are in parallel, so the total spring constant is just the sum of the two. Then you multiply it with x in the domain. And you take the Laplace, then this will be a capital F, 2 times k, then this will be in S domain also. Then output over input, our output is x. So x over f now will be equal to 1 over 2 times k. So this will be the transfer function of a spring with a massless body connected to that. In general, a zero order system, the form of a is in the form, in general, a zero order system is in this form, a is of 0 times our input or output, which is c of t, let's name it c, then this should be equal to another constant b, and the input, which is r. And if you take the Laplace of this, it will become f of s, or c a of 0, capital C, b times r, then output over input. Output is c divided by input. So this is just equal to b all over a of 0. Or this is just a constant k. And this k, we call this one the constant gain. Constant gain. Or static gain. Or they also call it static sensitivity. Static sensitivity. Or static gain. Can also be called static gain. And for this example, for a mechanical system, so the static gain is 1 over 2 times the spring constant. It's a different k here. This is k of constant gain. This is a k for spring constant. For a inverting op-amp, this is the static gain. And also for non-inverting op-amp, this is the static gain. They are all constant. They does not change with respect to time. So that is a zero order system. For another one, the zero order system, we have, how about if we have a first order system? Zero order system is a differential equation that has zero order, or in other words, it does not have any differential, because if the zero order, it's raised to 0, any number raised to 0 will be just equal to 1, constant. So here, in a first order system, we have now a differential equation because it's raised to 1, the degree is 1. So in general, again, in general, the form of a first order system is in this form, a is of 0 times the derivative of the output with respect to time plus another constant, and this is equal to our input, r of t. So this is the general form in time domain. So if we solve for the transfer function of this kind of systems, you take the Laplace, of this. So we have a result. This will be a of 0. And the Laplace of a derivative, remember, if we can also assume that c of 0 is equal to 0 here. So this means that we always assume that the initial condition is 0. There's no initial condition. There's no initial position, if it's position, initial charge, if it's charge, or voltage, or current. So A0, this is just A0 times S times in S domain now, plus 0, or C of 0. But C of 0 is 0, then just use this one. Then plus the Laplace of A1 times C. So let's make it capital C. And for the output, this is just R of S, or input. Then we can factor out that C. So we have A0S plus A1. And this is equal to R of S. What we want is the transfer function that is C of S, C, the output, all over the input R. So this will be equal to 1 all over this one, A of 0, S plus A1. We can also rearrange this so that if later on, if we want to go back to T domain, we can just directly use the formula to take the inverse Laplace of this one by multiplying 1 over A0, 1 over A0. So we can say that the transfer function output over input is just 1 over A of 0 all over S plus A1 over A of 0. So this is now the general form of the transfer function of a first order system. Now let's take an example on electrical system in electrical. So what are the examples of a first order system in electrical? We have the RC circuit or RC network. This is a first order system. RC network. So for RC network, we have a resistor R and we have a capacitor C. Then we have a voltage source. Let's just call it E of t. Then to solve for the transfer function of this kind of system, first we need what do we want to be our output. So there are different parameters here that can be our output. So this time, let's take the current as our output, I of t, instead of the voltage across the capacitor or the voltage across the resistor. But you can still do that. The voltage across resistor and voltage across capacitor as your output. So here, input will be E of t, the voltage source. Output will be the current I of t. So that's the first step, the procedure for finding the transfer function. The next is apply the theorems that you know. So here we apply Kirchhoff's voltage law into this loop. So we start with positive E, then minus the current multiplied by the resistance R, then minus the voltage across the capacitor. So we already discussed this in circuits 1. The voltage across the capacitor, the voltage across an inductor, the charge, and so on. This is just equal to 1. You can review them. This is just equal to 1 over C, the integral of I of t dt. And this is from 0 to t. Or you can still, you can remove that if you want. Because it's always, we always start at 0 up to a certain value of time. There's no negative for the time for initial condition. So if you have any initial condition, then you put it here. But we assume no initial condition, no initial condition. Initial condition. So we can just remove this from 0 to t. And this should be equal to 0 according to KVL. The next step, apply Laplace. So let's take the Laplace. So this is small letter e will become capital letter E. It's of s. And we have minus, this is a constant r, you just multiply it with I. And this one is an integral. So how do we take the Laplace of integral? Instead of multiplying it by s, this time we divide it by s. So this will be 1 over s times c times I of s. And this should be equal to 0. Then rearrange. We put the output I of s at the other side of the equation. We can factor out now. So we have here plus r, then 1 over sc. Then at the other side, we retain that voltage. Then output over input. So output is I divided by input E. This is just equal to 1 all over this R plus 1 over S times C. But again, we need, it's more convenient for us to convert this or simplify this into this form. So we need to multiply. We can multiply the numerator and denominator by S over R. So that the S here will cancel out and the R here will also cancel out. So this will be, so the transfer function now will be G of S will be equal to, we can factor out at 1 over R, then S here, then all over S times this, so S plus, S will cancel out. If you multiply it with R, this will become 1 over R times C. And this will be our transfer function. We did this because if you look at this part, now, if you look at the table, Laplace table, you can take the inverse Laplace directly using the formula. So it's better to simplify the transfer function into this form. This is our a C network. Now for RL, we can also derive that in RL circuit. Take note here, if the voltage across the capacitor is the output, if you want this as your output, the voltage here, then your derivation here, this transfer function will not be valid because this is the transfer function if the output is the current. So for you to derive this, you need to use, instead of 1 over C IDT, instead of current, it should be in terms of V out. So there's no, in the equation, there should be no term that involves the current. So change all the current, it should be in terms of the voltage V out. And what's the relation between the voltage and the current? So V out is just equal to 1 over C, the integral of i's of t dt. So this is the relationship. So if you want to solve for I, the current is just equal to, if you take the derivative of this is just equal to C, the derivative of the output of the voltage across the capacitor with respect to time. So instead of the current here, you have a derivative dV out over dt. Let's do that in RC circuit or RL circuit. In an RL circuit, if you have an R, then we have an inductor, then the source voltage is of t. This is L. We have the current I. Now we want our output to be the voltage across the inductor, and let's name it V out. So this time input still E is of t, but this time our output now is V out of t. So we apply the Kirchhoff's voltage law again. So we have E of t minus the current times the resistor. Then the voltage across here, which is V of out t, equals 0. Now we have two variables here. We have I and V. V of out. So we need to change this I in terms of V of out so that we can apply Laplace transform later on. So what will be the relationship between the two? So we know for inductance or inductors, the voltage across an inductor VL is just equal to the product of the inductance times the change in current, the IDT. But we want to solve for i's of t, so you just take the integral. So this one L di will be equal to VL dt. Then this will be, so we integrate both sides. So the I now, I of t, and again assuming there's no initial condition here, 1 over L, the integral of that voltage dt. So here, let's change that current in terms of this one. So we have the equation now will become is of t minus that one, I times R. So our I is this one, so it will become R over L times the integral of that voltage, which is V out, V sub out dt, then minus V sub out t equals 0. And if you look at the equation, there is no current in the equation. And it's only in terms of E, which is the input, and V out, which is the output. So the equation now is okay to take the Laplace. So taking the Laplace, so we have here again E of t will be capital E, and this is an integral, so this will be R all over S times L times V sub out in S domain, and minus V sub out in S domain equals 0. Rearrange it again to solve for V output over input. So on the other side, we have V out, we factor out that V out, then we have R over S times L plus 1. And this should be equal to the input E. And V out over input, now V out over the input E, now will be equal to 1 all over R over S times L plus 1. And again, we need to simplify this by, we need to multiply the numerator and denominator. We need to remove s at the bottom. So we need to multiply it by 1 over s. Then we still need, or that's already okay, 1 over s and 1 over s. Then this will be equal to 1 over s all over, s will cancel out, so times s, so this will be s plus r over l. So this will be our transfer function g sub s of an RL circuit with the voltage across the capacitor as an output. Okay, so this is for first order system in electrical circuits. How about in mechanical? What's an example of a first order system in mechanical system? There are many examples for this. We can have the uh, temperature, the transfer of temperature from one form to another. We can also have the other one, the liquid level, liquid level system, a more realistic uh, application. So a liquid level is just like this one. You have a container. This is your container, a tank, water tank, or anything that contains water. Then at this tank, we have a hole that a water will go through. So this is a water here. Then we have entering a pipe. It can come from a motor or something. So we have here an input flow rate Q. Then we have an output Q here for the flow rate. Q is the flow rate. Then if the cross-section area of this system or this tank, let's call it A, the cross-sectional area. If it's a circle, then it's pi r squared. It depends on the shape. And we can also name the height of the water. So it's changing to be letter H. So it's changing. H here is a variable. And now our conditions. H, I want H to be my output. I want to control the height of the water. But how do we control the height of the water? By changing the flow rate of the water coming or going through the water tank, or that is just Qn. That is my input. I want to control the height. What should be my input so that my height will remain at this point? So we need to develop or determine the transfer function of this in order for us to predict what will happen. And before we do that, we in P6, Q out, we have a Q out here. This is proportional to H. The higher the level of the water, the faster the flow rate of the output of the water tank. So if we change that, we can remove the proportionality symbol and let's just multiply it by C times H, where C is the constant of proportionality. And you can determine that in, if you go to P6 or mechanical or fluid dynamics, there are so many formulas in determining that. So in this section, I will just name it C as a constant. Then another condition, formula here, the total accumulated volume in the tank. How do we determine that? We determine that by subtracting the input flow rate with the output. You remove the outgoing. This is the incoming volume flow rate. You take out the output. Then the remaining, the difference is the accumulated volume of that. And how do we solve for that volume accumulated? This is just if this is a cylinder, then that's just the volume is just equal to the area of the base times the height. And it all also true whatever the shape of the base. We just name it by A. And that's just the A, the area, then we multiply it with the H. But this time our H is changing. It's changing with respect to time. So our volume flow or total accumulated volume will also be changing with respect to time. So instead of multiplying by H, we multiply it with the derivative of H with respect to time. Then here, I don't need Q out because my output is H, not Q out. My input is uh, Q in. So I need to remove this Q out here. And we already have a formula here. So we just substitute that. So we have Q in minus C times H equals A dH dt. And if you look at this, we have a Q in, that's our input, and our output is H. So we can now take the Laplace of this equation. Remember, C here and A are constant. A is the area, cross-sectional area of the tank will never change. So we can now take the Laplace. So this will be Q in S domain minus C in S domain. And for this is a derivative. So you multiply it by S, H of S. Then rearrange it again. We want output over input. Our output, remember, is H. So I need to move this one the other side, then factor out that H. So we have A is of S plus C, that constant, and this should be equal to the input. Then output over input, so H of S over Q in now will be equal to 1 all over A of S plus C. And this is a first order system. So we need, again, to multiply this with 1 over A. 1 over E. So the transfer function now of a liquid level will be 1 over A all over S plus C all over A. So this is an example of a mechanical first order system. And after this, the next one will be second order system, and they are more complicated compared to this first order and zero order.